Did you?
I just said,
No, him.
I don't know about my room.
I just think we get on.
Oh.
Shall we? Yes? All right, well, everybody get a copy of the notes? Yes? All right, so the idea behind me having these as a handout is so you can pay a little more attention to what's going on as opposed to writing down what I am putting up here. Although I will probably reproduce a lot of this on the board, all right? Let's start off with some preliminary stuff. Absolute values and just what they mean. So if somebody, if you were to write down the absolute value of x is less than 2, then there's really like a little 0 next to this, x minus 0. And so what you're saying is that the distance between some value, x, and 0 has to be less than 2. So if I come over here to the number line, and I choose this to be x right here, is the distance between x and 0 less than 2? Is that distance smaller than 2? Yes? If I pick an x value over here, is that distance less than 2? Yes, right? It's a distance, right? We're measuring it as a positive number. If I pick an x out here, the distance between 0 and x is greater than 2, so that would not work, right? So what we have is basically any number in here, right? But not 2, right? And not negative 2. So the way we'd write that is negative 2 to 2, something like that, right? X must be an element of that set of numbers. X belongs to that interval. So what I put on your notes is to remember that when you're looking at this, a way to convert it directly over to interval notation is to write it as x must be less than 2, but then greater than negative 2. Right, this is probably the big point, is how to convert that to this. Right, we'll be using that throughout the rest of the class. Is that all right? Any questions? No? Pretty straightforward? Okay. Now, power series. Yes? No. Yeah, no, this does not. Okay, so what is a power series? Well, according to what I wrote down here, a power series is a series starting at n equals 0, not 1. We usually started it at 1, right? But a power series starts at 0, goes to infinity, c sub n, that's multiplication, times x to the n, where, and I didn't put this here, oh yeah, I did. X is a variable, and c sub k are numbers. For k equals 0, 1, 2. So what you have, if you were actually to plug in numbers here, right, or plug in n equals 0, then n equals 1, this sum would become c sub 0, x to the 0, plus c sub 1, x to the 1, plus c sub 2, x to the second, and so on and so forth, right? So what we have is a series, right? It is a series, but it is a series of powers of x, right? Each of these terms is a power of x. And that's where it gets the name power series from. It's just a bunch of powers of x added up together forever. Now, the c sub 0, the c sub 1, the c sub 2, these are just numbers, and it depends on the problem. Every problem is different, what these actual numbers are, right? These may, if they're all 1s, then it's a certain type of power series. If maybe this one is 1 and that one's 2 and that one's 3 and then that one's 4, then that's a different power series, all right? But any series that has this form is called a power series. With me? Just one okay or yes would be? All right, thank you. All right, thank you. So if I fix an x value, so let's fix an x. What do I mean by that? Yeah, just plug in a value, right? Just something. Don't tell me what it is, but I'm going to fix it. That means you're not allowed to let x change anymore, right? Don't let it change. X is fixed. Then if I write out a power series like this, which we just said was c sub 0 x to the 0 plus c sub 1 x to the first c sub 2 x squared. Then if these are all numbers, right, x is fixed, if that's a number and that's a number, then the two of them together is a number, and then another number, then another number, then that's just a series, right? Once we fix x, this is just a series, which is what we spent the last couple of sections on. It's just a series of numbers, and therefore it could diverge, it could converge. It depends, doesn't it? If it's a geometric series, it would converge. If it's a harmonic series, it would diverge, right? But I'd have to know what the x is, and I'd have to know what the c's are, which each of the c's are, in order for me to determine that, yeah? Okay, so if x, this is, I'm about midway through the page here. If x is a value for which the series converges, so if we fix x and the resulting series converges, then it goes to a number, right? Yes, it goes to a number. So I could define a function f of x to be equal to this power series. Now let's try and understand what the heck I'm saying. Go back to when you first started learning about functions way back in the day. F of x is x squared, right? The whole idea was that you plug in an x, it spits out an answer, right? You plug in an x, different x, it spits out a different answer. You plug in 2 here, you get 4. You plug in 1, you get 1. You plug in 0, you get 0, right? Input, output. Yes? If I give you a different function like f of x is 1 over x, then we can do the same thing. Plug in a number, it spits out a number. Except what?
0.
At 0, 0, this thing is undefined, right? We have the same exact concept here. If we fix an x and this series converges, then it has a number that comes out, right? So you plug in an x, it spits out a number out here, right? This series, the sum of this series is the number that comes out. So I have an input and an output. Therefore, I could define a function to be this series, this infinite series, as long as what I'm plugging in creates a convergent series. If it doesn't, right, if the x I plug in does not create a convergent series and it makes this diverge, it would be similar to trying to plug 0 into this function, where it would be undefined. If the series diverges, then the function is undefined there. Does that make sense? Kind of? Yeah. We have to get into some examples, obviously. So if x if we fix the x and the series converges, then we can define this f of x to be this power series. It's a well-defined function. Well-defined meaning just like that's a well-defined function. If you plug in an input, there is an output. It's well-defined. All the values, okay, all the values of x that you could ever get together that would make this converge would be called the domain of f. Just like over here, the domain is everything that makes this make sense. It would be all x's except what? 0 here? Here, the domain is every x that makes that converge. Things that are not in the domain would be the x's that make that diverge. All right. So sometimes this is referred to as an infinite polynomial, right? Polynomial functions have powers of x in them, don't they? but they're finite. This is referred to as an infinite polynomial because it goes forever. All right, so we're going to start with our first example, which is a major example. And that is, I'm going to define a power series now for you. And I told you for a power series, the one thing you need to know is what all those little C's are. Right? What are all those little C's? Did you see notes? Okay. So I'm going to say let C sub k equal 1 for all k. Oh yeah, in my notes, this right here means for all k. That means for all. All right? That's not my notation, that's mathematical notation. All right? Upside down, capital A, for all. This one, anyone know what that is? There exists a k, this is for all k. For you math majors, you'll see more of that. All right, so here we go. We know all power series, right? Look like this. C sub n x to the n, right? But I'm telling you that every C sub k, is always 1. Then if I were to write this power series out, right? If all the C's are 1s, then this just turns into what? What's this? X to the 0, which is 1, plus x squared plus x cubed plus forever, right? That's what that would be. And then I say in your notes, do you see that that is very similar to a series that we studied before, which looked like this? A plus AR plus AR squared plus AR cubed plus dot, dot, dot. Geometric series, right? Here for us, what would A be? A would be the constant, which for us in this one would be what? 1. And if I let R actually be equal to X, right? So if I take a geometric series and I tell you A is 1 and R is X, wouldn't you come up with this? Yeah? So when would this converge? When would this series converge? When R is less than, absolute value of R is less than 1. But for us, we're not using R, we're using X. So wouldn't this converge if the absolute value of X was less than 1? Yes? Which I think I probably state on the back. So this series, I'll go back to red. This was just to get you to see that this looks like a geometric series. Therefore, sum n equals 0 to infinity of x to the n converges if the absolute value of x is less than 1, right? Now, does everyone see that what I did here was replace the c sub n with 1? Yes? Every one of those c's was 1. So in the formula, I just replaced the c sub n with 1. So everyone agree that that series converges as long as the absolute value of x is less than 1? Yeah? Yeah. And it diverges when? This will diverge if the absolute value of x is greater than or equal to 1. Now, I don't have this in the notes here, but I want to ask you a question. What is the domain of the function f of x if I define that to be the sum n equals 0 to infinity of x to the n? So I've defined a function to be an infinite polynomial, right? A power series. And I'm asking you for the domain, which is equivalent to asking you what? For what values of x? What? does this converge? So what's the domain of this function? Absolute value of x is less than 1, but how could we convert that over to like an interval notation? -1 to 1, right? This would be the domain of that function. So that means if I pick any number in here and I plug it into this function, I plug it into here, it will spit out a numerical answer, won't it? As long as my input comes from here. We could take a pretty simple example, and I could ask you, what's f of 1/2? So input, output, right? So is that 1/2 in the domain of the function? Yes? So this becomes sum n equals 0 to infinity. Replace this with 1/2, right? And what is that? It's geometric series. That'll converge, right? We already know it's going to converge. Is this one of the proper formulas that I can go straight to the a over 1 minus r? It is. If it's n up here, it has to be zeros to start, right? And so this actually does converge. What's a for us here? 1 over 1 minus r, I mean not r, sorry, x, which is 1/2, and that's just going to be 2. You all follow? So if I were to graph this function, right, if I were to ask you to graph f, you would be able to tell me that you can only draw your picture where? Between -1 and 1, right? That's the only place it would exist. And if I plugged in 1/2, I would go up 2 and I would draw a dot, right? And now I could plug in, I don't know, let's plug in 0. What would happen if I plug in 0? You just get 0, 0 plus 0 plus 0 forever, right? You get 0. And you could connect all the different pieces. You would have a graph of this function. Do y'all see that? Y'all are like, I don't know. It looked like you already had a couple of plates of turkey. We are defining a new type of function in this class right now. It is called a power series. It is a function. And it's important to understand that those functions' domains are defined by what makes the series converge. What about if I try and plug in 2? You can't, right? Does that mean that there's a dot, or just means there's no picture, right? There's no graph. There's nothing happening over here. Okay. I hope that's kind of enough to get us started. So the x is going to determine whether or not we converge, right? That x value makes all the difference. Now, we're going to move to what's called the general power series, which is called the power series about A. And it's the same formula we just had. The only difference is instead of having just x to the n, we have x minus a to the n. So do you see right here is a linear expression in x? What was the power series we just had before? What was a for us? It's the number, I'll put it down so we can see it. This power series that we just studied just a second ago. What was a? Careful. X minus 0 to the n, right? So this would be a power series about what? About 0, right? As opposed to something like this. I'll give you another example below. N equals 0 to infinity, x minus 2 to the n. That would be a power series about 2. It's just a slight little change. All it does is just kind of moves our our series over. Do you remember with functions when you subtracted a number on the inside, what it did? Shift it to the opposite of what you think, right? So if you take away 2, it moves the whole picture to the right 2. If you add 2, it moves it to the left 2. It's the same sort of thing. It's just moving our function left or right. Understand? Let's look at this one right here. I want to compare right now real quick. I want to compare this one to this one. What's the difference between those two? I mean, don't tell me that one has a -2. I mean, like, I get it. If I call that f of x and I call this g of x, what's the main difference between the two? It shifts the domain, right? The domain is different. For this to converge, what did we need to happen for this to converge? The absolute value of x had to be less than 1. What has to happen for this to converge? The absolute value of x minus 2 has to be less than 1. Right? What's in here, right? This was the r, wasn't it? This has to be less than 1 for this to work. Understand the difference? I want to continue that over here. Tell me what the domain of G is. What's the domain of G in interval notation? We'll start with this. That's what we know, right? Do you remember what I did in the beginning of class? I said if you saw that, it turned into this, right? Isn't that what I said? So for this one, you're going to put x minus 2. You're going to put less than 1. You're going to put greater than what? -1. So if you have the absolute value of something is less than 2, that means it's less than 2 and greater than the opposite of the 2. So if this is less than 1, that means x minus 2 is less than 1, but it's also greater than the opposite of 1, which is -1. See how I did that? Now solve for x here. Add 2, add 2, add 2. Got me? So what do you get? 1 less than x less than 3. So in interval notation, the domain of G would be, what, 1 to 3? What was the domain of this one? -1 to 1. Isn't that, if you move this to the right, 2, 1, 2, you get this? Okay, so that was like a shift in our domain.
So the actual range of the domain never changes, but just the...
That's correct. Well, the range values will be the same for both.
Yeah,
Where they happen will be different, but yeah. The outputs will be the same. It's just like if you take a parabola and move it over, right? The picture still looks the same, just been moved. All right. So let me show you that general power series again here. Remember the ultimate question, all right? The ultimate question here, and please pay attention, I put C sub n back in here, so we're not working with that example anymore where that's a 1, okay? Just a general power series right here. I want to know what will make this converge, right? That's what I want to know. If I let x be equal to a, right? So if I say, what's f of a? If we call this f, sorry. What's f of a? Is what? This is a minus a. It's 0 to any power 0 times who cares? 0 added forever is 0, isn't it? Doesn't that converge? I mean, I plugged in a, right? And I got a number out. So anytime I have a power series, if I plug a in, it converges. The big question for us is what if x isn't a? Right? So if x equals a, convergence guaranteed, right? Convergence for sure. If x is not a, that's what we want to know. That works for every power series out there. All right, you ready to look at our first example? Yes? I mean, like our first real example, like a homework problem example. Yeah? All right, so here's the first example. For what values does values of x, you have this written, does this converge? Sum n equals 0 to infinity of 2n plus 1 times x to the n over n factorial. Well, before we answer this question, let's make sure it is a power series. All right? Does this look like a power series? So can I rewrite this as 2n plus 1 over n factorial times x minus 0 to the n? Is that fair for you? That seem okay? Seem logical? Can you tell me what c sub n is in this? 2n plus 1 over n factorial, right? Can you tell me what a is in this problem? 0, right? A is 0. Anytime you see x to the n by itself, a is 0. So it's a power series about 0. This is just to get you to see that we are dealing with a power series, yes? But the question is, for what values of x does it converge? Well, this goes back to last section. When we have series, how do we check series for convergence? What do we have in our toolbox? N-term test, comparison test, limit comparison test, ratio test, root test, integral test, right? All these different tests. The thing is, we have never had to deal with this x before, right? If it were just this, we would be doing a problem from your test, basically, right? But now we have this piece that throws kind of a twist into it, yes? I told you when we covered ratio test that it was probably the most important test. And the reason why it's the most important test is because we liked the ratio test when we had powers, right? N was our power. We like the ratio test. And if you're looking at a power series, you will always have a power of n, won't you? If it's a power series. So the ratio test is very useful for determining convergence of power series. So that's what we'd like to start with. All right? So someone remind me about the ratio test. What does the ratio test say? Yep. Right? If this is true, if that's true, then what's the conclusion? The series converges, right? Absolutely. It's all on your sheet of paper, but that was the conclusion, right? And the big key is that we want to know when this converges, don't we? Yes? So don't we want to know when this is less than 1? So let's set this up. Let's take the limit. And let's figure out what would make it less than 1. If we can figure that out, then we will have determined where, for what values of x it converges. All right, here we go. I'm going to set up the limit as n goes to infinity, absolute value. Now, a sub n plus 1 is this expression, right? The entire thing with n plus 1 plugged in, right? And I hope we've done this enough that you can follow my next line. It'll be 2n plus 3. So remember, I just replaced that n with n plus 1, distributed the 2 over, added the 1, right? Then when I replace this power with n plus 1, I can rewrite it x to the n times x. So that's already splitting it apart. Do you all follow me with that? Over, when I replace this n with n plus 1, it becomes n plus 1 factorial. But what do we always do with that? We peeled off an n plus 1 and n factorial. Now, I may have moved too fast. I don't know. Just remember this equals this, and n plus 1 factorial equals this. Did I point this out enough when we were covering it? Like, did I stress it enough that we would be using this a lot to the point that you can do this? Yes?
But I'm confused on the 2n plus 3.
He distributed the
I'm replacing that n
Okay.
with n plus 1. But the 2 has to hit that. So it's got to distribute 2n plus 2, 2, and then I had a 1 out here. So we're good with that? That's a sub n plus 1, isn't it? And I'm supposed to divide that by what? A sub n, which is this, right? But we talked about how that would become flipping. So next to this, I'm going to say times this flipped over. So n factorial over 2n plus 1 x to the n. Any questions? What do I need that to be for this to be able to converge? Less than 1, right? That's what I want. I want this to be less than 1. And that looks like a mess, but because of all the cleaning up I did, there's going to be lots of cancellation here, right? The x to the n's gone. This n factorial is gone. That's why we did this in the beginning, right? That's why we peeled this off, is because we could feel this cancellation coming. Could you feel it coming or not?
Nope.
No? All right, so this equals limit. Now please pay attention and follow what I'm about to do. I'm going to get everything that has n together right here and anything that has x over here. All right, I'm going to separate the two. So let's see. On the top, I have a 2n plus 3, right? So I'm going to put that right here. And then on the bottom, I have, let's see. In terms of n, I have n plus 1 and 2n plus 1, don't I? n plus 1 and 2n plus 1. And then separated from that, on the top I have x, and on the bottom I don't have any x's, right? So is it fair for me to just put x out here like that? No? That's same as x over 1? Right? Isn't that the same as x over 1? We good now? Okay. What variable is the limit affecting? N, right? This limit has nothing to do with x, does it? Just this n. So what I need to figure out is what happens here if n goes to infinity. I get infinity over infinity, don't I? So I'm probably going to want to use L'Hopital's rule. But before I do that, let me rewrite this. Let's expand this. You know, multiply it through. You get 2n squared plus n plus 2n plus 1, right? And then you group those together. You get 2n squared plus 3n plus 1. Right, that's really what the denominator is, isn't it? Now, if I do L'Hopital's rule one time, what is my new limit going to be? So if I do L'Hopital one time, I get what? Derivative top, 2 over 4n plus 3, and then still next to it times x. I need that to be less than 1. What does that go to? This goes to fixed number over infinity, right? What does that go to? 0. Doesn't it? So this is headed towards absolute value of 0 times x. And I need to know when that's less than 1, right? When will that be less than 1?
Always.
Always. Why? So x, remember I said this in the beginning. You have to fix an x, right? If I fix an x, x is not allowed to move now, all right? If I tell you that's a fixed number, and I'm going to multiply times a number that gets really small, It doesn't matter what x I ever pick. This is eventually going to get small enough to kill off x, isn't it? And make it less than 1. What does this mean? It converges. See, the question was, for what values of x does it converge? All values of x. It doesn't matter what I plug in for x, right? This is always going to be less than 1. So it converges for all values of x. Therefore, series n equals 0 to infinity of 2n plus 1 times x to the n over n factorial converges for all x. How would you write that in interval notation? Negative infinity, yes, less than x, less than infinity. But as an interval, we would just say negative infinity to infinity, right? So we would say. In terms of a domain, if we were to call this a function, right? If I were to say, hey, everyone, I want to define that to be the function f of x. Then if I draw this function, it's going to exist everywhere, isn't it? Everywhere on the number line, I'm going to have some value come out, aren't I? It's not like the previous example where we were just between -1 and 1. This one is defined everywhere. With me? Okay. So that's our first one. Let's look at another one. Same question. For what values of x does this one converge? N equals 1 to infinity of 3x minus 4 to the n over n squared plus 1. This is a power series, yes or not? Yes or no? Is that a power series?
No. Does n have to start at 0 for it to be a power series?
That's a great question. Does it have to start at 0? Your first term, right, when you write out a general power series, n equals 0 to infinity of c sub n x to the n, right, like this. Your first term, when you plug in n as 0, this is always a 1. And so you get c sub 0, which is just a number, right? So the first term of a power series should be a constant. This one right here, if I plug in 1, the first term is not a constant. But there is a constant in front of it. What is it? Plus what in front of it? 0. So this, even though we're saying that all power series should start out with a constant like this, this one, the constant that's out in front is actually 0. So it's okay that we're starting at 1. To answer your question, we're okay. Yes. All right. So it is a power series. It's a power series about what? Uh-oh. So remember, for general power series, we said x minus a to the n, that this would be a power series about a, right? Do you notice what the coefficient on x is here? 1. So that doesn't look like this yet. So how would we
Set that equal to 0. 4/3?
4/3?
No, I mean, you just define
It'd be hard to pull a 3 out right here only because the n power wouldn't allow you to pull it, right?
You can set it equal to 0. That little in the parentheses.
Yeah, set 3x minus 4 equal to 0. And what would you get? 4/3? So this is going to be centered about 4/3. See, because what you want to know is what would make that 0, right? Remember when we said f of a should always be 0? F of a should always be 0 for every power series. The question is then, to say that this is a power series about a means I need to figure out what x is that makes this thing 0. And so you set the inside right here equal to 0, and you get x is 4/3. So a is 4/3.
So you don't want to try and change the actual function itself.
That's right. You don't want to try and take things out. Just set this linear expression equal to 0, and this right here is a. So this right here is a power series about what? About 4/3. What do they mean by about? We'll see, hopefully in this next problem, you'll see what they mean by, why are they saying about 4/3? Right, that's kind of a weird language. It's going to be the center of where, you know how we're going to have a domain? That is going to be the center point of the domain.
Like, is it going to curve?
What will? What?
Like on functions, there's a center point and there's a max or a min on that point.
Oh, well, we don't know what these look like. I mean, what we're about to learn, if we get to it hopefully, is basically every function you've ever known in your life has a power series for it. So think of any function that you can think of right now. There's a power series for it. So we know those can look like all sorts of things, right? So it may have a max, may not, may have. The sine function is a power series. So think about what that looks like. All right. OK, so it's about 4/3. Let's do a ratio test. Let's figure out where it converges, right? So for the ratio test, I want to take the limit as n goes to infinity of, I've got to plug n plus 1 into that first, right? 3x minus 4. What should I write? You want me to write n plus 1, or you want me to split it now? Split it, n, and then what goes here? 3x minus 4, right, to the first power. And then over, now be careful here, n plus 1 squared plus 1. That's what happens if I replace that n with n plus 1, right? Then I have to divide that by this without, just plugging n into it, which is the same as multiplying by the reciprocal. So what goes over here? What goes on top? N squared plus 1 on top, bottom. 3x minus 4 to the n. And what do I want about this thing? I want it to be less than 1. Do y'all remember what happens if this is greater than 1? Diverges. What if it's equal to 1? Fails. Test fails, right? Do you remember that's a huge point we're about to discover in just a second, that's a huge issue for us, all right? Right now we're saying I can guarantee you that this power series will converge as long as I can determine when this is less than 1. So let's try canceling stuff. Right? Is that it? That's all that cancels, right? You can multiply this all out and collect, but you better not cancel the n squareds. Right? Let me write one more line. Limit n goes to infinity. We've come this far, so let's not do crazy algebra now, all right? N plus 1, I'm putting all my n stuff on this side. N plus 1 is the only thing I have in terms of n, right? On the bottom, I have this. Now, I'm going to expand this, which is n squared plus 2n plus 1, but then plus 1, so n squared plus 2n plus 2. Everyone agree that that's this? And then what's over here that has the x's in it? 3x minus 4. I need that to be less than 1, right? Which one? Right here? I multiplied this out first, which is n squared plus 2n plus 1, and then I added 1, and that gave me the 2. So we're all okay with that line? Yeah? Let n go to infinity. L'Hopital? We're going to get a 1 here. This is going to go to 1. Is that all right, everyone? So here's where we are. No more limit, right? Because we took the limit. We are at the absolute value. This turns into a 1. As n goes to infinity, that goes to 1. So the only thing left in here is 3x minus 4, right? Absolute value? Less than 1. Yeah? As long as this is less than 1, this thing converges. But I'd like for it to be given to me in an interval. So how do we get rid of the absolute value? We just did this a couple of times. We rewrite what's in here. We rewrite this. But on the other end, we put what? Greater than -1, right? Now, let's get x in the middle by itself. So what I'll do first is get rid of the -4. I'll add 4 to everything. If I add 4 here, here, and here, I get what? 3 is less than, 3x is less than 5. And now I divide both sides by 3. Or both sides. Divide everything by 3, I'm sorry. And what do you get? 3, 3, 3. 1 is less than, x is less than 5/3. Right? And just so you see something real quick, this is 3/3, right? What's the number right between, right in the middle of 3/3 and 5/3? 4/3. So if you were to graph this, here's 1, here's 5/3, right? Oops. 5/3. Right in the middle is 4/3. And I know that anything that you pick in here and in here will work, right? This is the domain of my function if I were to look at it as a function. So that's why they say it's a power series about 4/3. 4/3 is the center of your domain. With me? So everyone in here agrees right now that this will converge, for sure. It converges if x is greater than 1 and less than 5/3, which is the same as the interval 1 5/3. Everyone agree with that? Yes? And that came from asking ourselves this, right? That's where that came from? Less than 1 came from the idea of the ratio test, tells us convergence if it's less than 1. And I said we have to also take into account one other situation, if it is 1, right? If this equals 1, then the test would fail us, right? It doesn't tell us it diverges. It would just fail, right? When would this equal 1? When would it equal 1? If I change that to an equal sign, and you try and solve this, this actually becomes 2 different equations. It becomes 3x minus 4 equals 1, 3x minus 4 equals -1. So it's the same as the inequality. You know how you had 2 different inequalities, one with positive and one with negative? A strict equation becomes 2 different equations. And if you solve this, guess what you get? 5/3. And if you solve this, guess what you get? Hold on. Bring this over. You get 1, right? Do those numbers look familiar? No? Never seen those before? They're the endpoints of the interval, aren't they? So listen. The ratio test told us that this interval, for sure, it converges. Can you tell me if it converges at 1? If I let x be 1, does our power series converge? Do you know? You don't know, right? How about at 5/3? Do you know? It could, though, right? It could? So guess what we have to do now? We have to check each one. We have to check now. We know for sure it converges on the inside of the interval, but now we need to check the endpoints. We know anything outside for sure won't work. So I need to check the endpoints. On the final, if you fail to check the endpoints, you're missing a major portion of this problem. If all you do is a ratio test and give me this answer and fail to check the endpoints, you're leaving out part of your major piece of the problem, right? So let me just start. I'll start with let x be 1. All right? Let's start with the left endpoint. I would like to know if I let x be 1 into that power series, what happens? So does everyone remember what the power series was? Sum n equals 1 to infinity. It was 3x minus 4 to the n over, was it n squared? Plus 1? That was the original power series as presented to you at the beginning of the problem, right? What I'm doing now is I'm saying, all right, sure, go in there, let x be 1 right now. Let's let x be 1. What happens if I replace x with 1? What do I get? 3 times 1 is 3, minus 4, negative 1. So I get negative 1 to the n over n squared plus 1. And I heard you say it. Now we are doing what we did last section. See, there's no more x in there. X, we replaced it with a number, didn't we? So this is an alternating series. How would you show me whether or not that converges or diverges? How would you do that one?
1 over n plus 1. You separate it?
You want to separate it? You want me to write like negative 1 to the n like that, and then 1 over n squared plus 1? Okay, and then what do you want me to do with that? Solve it? Just solve it? Okay, so what are you using there? You're doing the right thing, but what is it called? Alternating series test. Would you like to try the alternating series test here? It's an alternating series, so maybe the alternating series test. So now you have to go call on that alternating series test. And you have to remember the two things you have to show for the alternating series test. What are they? So you have to identify the part of the series which we call b sub n. And you have to show that 1, what? B sub n is greater than b sub n plus 1, which means that you have to show it's a decreasing sequence. And the second thing you have to show is that the limit as n goes to infinity of b sub n equals 0. Right? You got to go walk around. Just go walk all the way down the hall, go around, come back. Go get your blood flowing, seriously. Because, I mean, you're like in and out. All right. So I'm going to show, I always like to show 2 first, because 2 is like usually the easier thing to show. I mean, look, you can just look at that, right? N goes to infinity, that goes to 0, right? But I'll show it. 2, limit n goes to infinity of 1 over n squared plus 1 equals 0. Check. I've got the first condition of the alternating series test done, right? The second condition is to show, or first condition is to show that it's decreasing. So how do I show it's decreasing? This, right? Do that and show it's greater than 1 over, does anyone remember what we got when we plugged n plus 1 in here? Yeah, n squared plus 2n plus 2. If you don't remember where that came from, just go back and look at your ratio test. We did that earlier. And then you can do that thing. Like that. And n squareds cancel. 2n greater than negative 1. So I just left the 2n here. Brought the 2 over. Is that true? I hope so. 2n is definitely bigger than negative 1. So we've shown it's decreasing, right? Therefore what? Therefore this converges, right? So therefore, that converges. Which means what? X equals, what did we plug in to do this? We were plugging in 1. So that means we do want 1 in our domain or we do not? We do, because it makes it converge. So now our interval is adapting. We knew up to this point it was everything between here and here, right? Now we're saying you can actually have it be 1. So this is now changing to be this. What we still don't know is whether or not that is closed, including 5/3 or not including 5/3. Do you understand what we're doing? Okay. Do you see how within this one problem, you're going to be doing 2 different series tests? Like I had to do alternating series test. Now when I go to the other endpoint, I'm going to have to do something else. But that's all on top of the other stuff that's built into the problem, right? So what? Yeah. No, I'm just trying to get you to see how it builds on what we did already. How it's, you're going to be asked 2 convergence problems within 1 power series problem. It's built into it. Well, unless you look at the previous example, why didn't we check endpoints on the previous example? No? Because it converged for all x. So remember our interval was everything? And so you don't have to check endpoints when it's everything, right? Okay. All right, so what am I going to do now? Let x be 5/3 and go rewrite the entire series. The way it appeared when it first came out, it was 3, replace the x with 5/3, minus 4 to the n over n squared plus 1, right? So replacing that x with 5/3, and that's nice, isn't it? Somebody tell Ron to, all right, let Ron in. Thank you, Ron. We almost didn't let you back in. You laugh. I heard that. All right, so what's the difference between this problem and the previous one? Yeah, it's the top is really 1 to the n, right? Not negative 1 to the n this time. And then over n squared plus 1. But what is 1 to the n? I mean, really, what's 1 to any power? It's 1, right? And be careful, because this has always caught students, because they get so used to L'Hopital's rule and like indeterminate forms. They're like, well, wait a minute, you told me that like 1 to infinity was like an indeterminate form. And you have to understand, when we were doing L'Hopital, we were saying this part was approaching 1. This part's approaching infinity. This is not approaching 1. It is 1, right? If I plug in 5/3 and I put it right there, that is 1. It's not close to 1. It is 1. Okay. So that means the n power doesn't matter, does it? Now, we cannot do alternating series on this, can we? Because it's not an alternating series. It's almost a p series. Almost, but the plus 1, right? It would be really nice if it were. Comparison, though, we could probably compare it to a p series, right? N-term test would fail. If you do the n-term test, the limit of the inside of this will go to 0, which is inconclusive. So what do y'all want to do? How about we do a limit comparison test? You want to do a limit comparison test? I'm going to compare it to 1 over n squared. Compare to this series. And this series is a p series, right? P is 2, which means what? Greater than 1 converges. So I'm going to compare this to a convergent p series. And I'm going to use